This is the story all about how the Schrodinger equation applies to the free particle. What do we mean by a free particle? Imagine an electron, for instance, floating in the vacuum of space. It never encounters anything. It never runs into anything. How that enters the Schrodinger equation is that there is effectively no potential anywhere. So the time-independent Schrodinger equation, and we're back to one dimension now, so don't think about a particle floating around in the vacuum of three-dimensional space. It's floating around in the vacuum of one-dimensional space. The left-hand side of our time-independent Schrodinger equation is the Hamiltonian operator applied to the wave function. This is in some sense the total energy, which breaks down into a kinetic energy component here with the momentum of the particle squared divided by twice the mass, and a potential energy part here, where V of x is the potential energy that the particle would have to be found at a particular location. In the context of the free particle, where there is no potential, what that means is that V of x is equal to 0 everywhere. That means we can just cross out this term entirely. We don't have to worry about it. What we're left with then for our time-independent Schrodinger equation is minus h bar squared over 2m times the second partial derivative of psi with respect to x equal to e psi. Now we have some constants here and we have a constant here, so let's lump them all together. And I'm going to shift the signs around a little bit as well, so that what we've got is the second derivative of psi with respect to x is equal to minus 2me over h bar squared times the wave function. So I've just lumped all our constants together and multiplied through by a minus sign. Now, you notice the second derivative here of the wave function, giving you the wave function back. The fact that we're taking a second derivative suggests that the constant here perhaps is squared. So what I'm actually going to write this as is the second derivative of psi with respect to x is equal to minus some constant k squared times the wave function, where k, our constant, is the square root of 2me over Planck's constant. So this is the differential equation, and we ought to be able to solve this. This is relatively simple compared to the structure of the differential equations we got from the harmonic oscillator. So how do we solve this? Well, what we have, second partial of psi with respect to x is minus some constant squared times the wave function. Taking the second derivative gives you a constant squared. That immediately suggests we look for exponential solutions. And it turns out the general solution to this equation is some constant times e to the minus I k x plus b e to the plus I k x. If I take the second derivative of this exponential term, I'll get a minus I k squared, which you know is just minus k squared, applying the rules of complex numbers, which is what we get here. So when I take the second derivative of this term, I'll end up with minus k squared times this term. And I get the same sort of thing here. If I take plus I k squared from the second derivative, that again gives me a minus k squared. So we're okay. This is our general solution. When we include time in this, since you know this is a solution to the time-independent Schrodinger equation, it's going to have time dependence given by the time part, the time equation that we got when we did separation of variables. What you end up with is psi of x and time now is equal to a e to the minus I k x times e to the I energy t over h bar plus b times e to the I k x e to the I energy time over h bar. And I've left off my minus signs here in the energy dependence, just conventional to include minus signs there. We can rewrite this a little bit as a e to the I k. Now, what I'm doing here is substituting in the definition of k, which if you remember was the square root of 2me all over h bar, expressing energy in terms of this k. And when I do that, what I end up with is this term ends up looking like h bar k squared over 2m. Substituting that in here is what we get from manipulating our constants here. If I do that manipulation, the first term here, instead of having this product of two exponentials, I'm going to write it as a sum in the exponent, x minus h bar k over 2m t plus b times something that looks very similar, e to the minus I k x plus h bar k over 2m t. So these are our general solutions to the full Schrodinger equation. Our full wave function is a function of both position and time. And these solutions are traveling waves. You can think about this as a traveling wave in the context of looking at this as a complex number. If I look at e to the ikx, for instance, as a function of x, you know what that does in the complex plane? It just rotates around in the complex plane. If I look at this as e to the ikx, let me redo that a little. Ik times x minus h bar k over 2m t. And I treat this as a function of time. Again, we just get rotation in the complex plane. We get rotation in the other direction, but that's not really all that important. What is important is that you can visualize this in, if you want to think about it in 3 dimensions, with some real part here, and, sorry, why do I say real and then write imaginary? With, say, the real part here and the imaginary part here, what we've got is something that spirals around the 0 point. Now, if I look at this as a function of both position and time, at every time I have this spiral as a function of position, say. As time increases, what changes about this spiral is the whole thing shifts, either in the plus x direction or in the minus x direction. And you can determine how that propagates by looking at the argument here. If I look at x minus h bar k over 2m t, if I'm looking for a specific point on the spiral, say this point, and I want to know whether it moves this direction or this direction, I can look at this expression here. This specific point on the spiral, as the spiral moves, is going to be represented by a constant value of this argument. And if all I'm caring about is what direction the wave moves, I might as well set that constant equal to 0. What that means is I can write this as x equals h bar k over 2m t. And this immediately tells me that as time increases, x increases for this specific point on the spiral. So in this particular case, the wave is going to the plus x direction. For the other term here, the relative sign of x and t is different, so you end up with a wave propagating in the opposite direction. So these are our traveling wave solutions to the time-independent Schrodinger equation, or to the overall Schrodinger equation, excuse me. To check your understanding, go back and review the definitions of these traveling wave solutions, and think about how the energy enters. Do high-energy free particles move faster or slower? Is the wavelength, in a sense the tightness of the spiral, shorter or longer? And is the time evolution, the rate at which the spiral rotates in time, faster or slower? What we did after we got our stationary state solutions to the Schrodinger equation for instance, the particle in a box or the harmonic oscillator, was examine the boundary conditions and determine whether or not we had quantization. This is where the free particle gets a little bit difficult to work with. The problem here is that v of x is equal to 0 everywhere. And I mean everywhere. There are essentially no boundaries. The fact that we have no boundaries means that we can have any value of that constant k, which means we can have any value of the energy, E. So we have no quantization here. That's a problem. It's not necessarily a problem directly, but it means that instead of what we were dealing with the particle in a box, for instance, where we had functions that were easy to represent, because there was a finite number of them, we could write a sum from n equals 1 to infinity of Cn times psi sub n. Same for the harmonic oscillator. We got a discrete set. We got a quantized solution. Now we have no quantization. So the framework that we built up for treating particles with quantized states isn't going to just directly apply. We'll have to do something a little different. The other thing that's different about the free particle is the normalization. The normalization condition we had for a wave function psi was that you multiply the complex conjugate of the wave function times the wave function itself, integrate from minus infinity to infinity, and I've left off my dx here. You should get 1. What happens when we do that here? Well, this normalization integral, if we're working with, just say, the term a times e to the, where did it go? E to the I k x minus h bar k over 2m t. If we're just working with this term, taking the complex conjugate is easy. The only complex part is this I here. And what we're going to end up with for our integral then, a being a constant, we can pull it out front, both the a star from psi star and the a from psi. We have the integral from minus infinity to infinity, dx, of the complex conjugate of psi, where we flip the sign here, and we've got e to the minus I k times something, which I'm too lazy to write. For psi, we get e to the plus I k times something that I'm too lazy to write, and it's the same something. These two terms, the arguments here, are the same, which means here I have a complex number times its complex conjugate. Since it's a complex number of modulus 1, I know this product is just going to be 1. So what I've got then is a star a times the integral from minus infinity to infinity dx, period. I'm done. And when you integrate dx from minus infinity to infinity, you get infinity. So this is a problem. These states are not normalizable. Anything I might do to try to normalize these by, say, setting this equal to 1 and solving for a, I would get a equals 1 over infinity, for instance. This is not useful. We cannot effectively normalize these states. This sounds like it has shot all of our framework in the foot, but it actually hasn't, because we can still use the framework of superposition. Superposition of these traveling wave solutions can give what are called wave packets. The bottom line, we can still write psi of x t equals 0 is a superposition of these traveling waves. We just have to be very careful about how we do the superposition. What these wave packets look like in the end, if I give myself an axis, is the wave function, the real part, might look something like this, where it's 0 for very large positive and very large negative values of x. The imaginary part might look something like this, where the full wave function only is non-zero over a specific interval. Over a limited range, for instance, or a limited domain, to use the mathematical term. When psi is only non-zero over a limited range like this, we can normalize it. What's tricky is how we normalize psi by making a superposition of non-normalizable states. And that's the topic for next lecture. So to check your understanding, here's a recap of what these traveling wave stationary states look like and what their properties are.